Hello people from the future, welcome to Normalized Nerd. In the last video, I have shown you how you can implement the simple linear regression in Python without using any libraries, and today I'm just gonna do that with logistic regression. So what is logistic regression and why we use it? Well, we use logistic regression to solve classification problems. So what is a classification problem? Well, let us have a look at this data. You can see this is a scattered plot of this data, and the data points belongs to two classes. One class is blue, another class is yellow, and this axis represents the x0 feature and this axis represents the x1 feature, and we want to just separate these two classes. So how we can do it? Well, the most intuitive thing to do is just to draw a line here and then say if we get a new data point that lies in this region, that is this side of this line, will belong to class yellow, and and any data point that will lie this side of this line will belong to class blue, and we just want to find this line. So how we can find this line? Well, let us just first write the equation of this line. So what will be the equation of this line? Well, by using these variables, we can write the equation as w0 plus w1 x0 plus w2 x1 equal to 0. And you can see that if we take a data point that lies on this line and then plug this data point in our equation, then it will give 0 because it just satisfies the equation, and any data point that lies in this region will give a positive value, and any data point that lies here will give us a negative value. And we are just going to exploit this fact to our binary classification. So why it is a binary classification? Because there are only two classes, right? Now at this point it may seem that okay, if we just can find this equation, and then we can easily classify these two lines, these two sets, right? But wrong. We need to do something extra upon this linear function. We need to add something non-linearity to it. So why we need to add a non-linearity? Because if we just use this thing and then use this condition, if this thing is equal to greater than equal to 0, then it belongs to yellow class, and if this thing is less than 0, then it will belong to blue class. Will that be a terribly unsophisticated thing? Because this won't give us any concept of its probability. Okay, because this number can be larger than 1 and can be negative also, but in most cases we want to deal with probabilities. So how we can find the probability of a data point to belong to a certain class? Well, we can just add a non-linear function, which is a sigmoid function, to this linear function. So let me just write the sigmoid function first. Well, this is the equation for sigmoid function. And what we are going to do, just let me write this as f of x, and we are going to predict y pred equal to sigmoid of f of x. And suppose we find this line, and then we get a new data point here, and if we just plug in this data point in this equation, it will give us a positive value, and then we are going to pass this positive value to our sigmoid function, and then it will give me a probability. So let me just draw the sigmoid function for you, that will be more clear. Okay, this is this z, and this is sigmoid, and the function looks like this, and this is the one which is the asymptote, and this is another asymptote, and this is 0, half, 1. So you can see here, no matter how large is z, this function never goes never reaches the 1. Actually it reaches 1 at infinity, and no matter how negative is z, it never goes below 0. So you can see that no matter how large the value of this, it will give us a value between 0 and 1, and this is exactly the probability. So in some sense, this function helps us to find the probability of a data point belonging to a certain class. And suppose we get a value like 0.99, then we can say that, suppose this point gives us a value of 0.99, then we can say that this point has a 99% chance of belonging to this class, and we can represent this class as 1 that I have represent here. And suppose a point here gives us a value 0.001, then we can say that this point has a 0.01% chance of belonging to one class. That is, it has a 99.9% chance of belonging to this blue class, right? So that is the concept of logistic regression, and we are going to find the weights of this line. So what is the weights? Well, these things we are going to find, because we need these three things to construct our lines. Okay, so how we can find this? Well, here comes the old concept of cost function. Let me just scroll this a bit. By the way, we represent the data points as a capital X. It is a matrix and it just contains the m data points, and this is the ground truth, and this contains the which class it belongs to, and this value y I belongs to, in our case, 0 or 1. Okay, and this is the vector of weights w0, w1 and w2, and we are interested to find this vector. Okay, so how you can do this? We are going to use the minimization of cost function. Now in the previous video I have shown you the cost function of square error, but in this case we don't use the square error cost function, we use this cost function, you can see, and this is called binary cross entropy cost function. Okay, and as usual, this yi pred actually represents the probability of a point belonging to class 1. Now to implement gradient descent, we need to calculate the partial derivative of our cost function with respect to our weights, that is w0, w1 and w2. And if you want to know in details about gradient descent, then you can see my other videos where I have implemented gradient descent in Python from scratch. So here comes our first partial derivative, which is the partial derivative of j with respect to w0, and turn your calculus sense on. So to differentiate this, we first apply the chain rule, and by applying the chain rule, this term will give us this term, and you can see that the partial of y pred with respect to w0 can be easily found from this thing, and which will be, so this term is actually equal to y pred times 1 minus y pred. You can refer to this side note where I have differentiated the sigmoid of z with respect to z, and you can see that this form is actually this form. So that's how I got this term from this one. And similarly, you can differentiate this thing also, and you will get this one. And after doing that, you need to do some simplification, and these two terms will be cancelled out, and then you will get a beautiful formula just like that. And this was all for the w0, and we need to do the same for w1 and w2 also. And in these cases, you can see that here we have x1 and x2 terms. So how these two terms are coming here? Well, actually, if you see the formula, then there is these two terms. Okay, so that's why we got this x1 and x2 multiplied here. So this was all we need for the gradient descent, and now we need to jump into the code where I will be showing you how you can implement the logistic regression along with the minimization of cost function and gradient descent. This is my IPython notebook, and the first thing we need to do is to make a fake data for our classification problem. So how can we make this? Well, we can easily make a fake data from the famous library scikit-learn, and there is a module called datasets, and there is a submodule, a sample generator, and we need to import make blobs. Well, blobs are basically acting as our classes. Okay, so the number of centers for our problem is 2, because we are going to have two classes, and the number of samples I am taking 20, so our m is 20, and number of samples I am taking as 200, so our m is 200. And these things like cluster standard deviation and random state you may put according to your desire. And the n features, that is number of features, we are taking as 2, as we have considered only two features in our conceptual portion, that is x0 and x1. Okay, so here is an interesting part. We are going to visualize our data. Well, you don't need to worry about the visualization of data, because there is no machine learning here. There is just some data visualization code, and you can easily find it on internet. And I'm going to post this code in GitHub, so you can also find it from my GitHub repository. So what is doing, basically it is doing a scattered plot and marking each classes with a different color. So let me just run this code. Okay, so this is our data represented in scattered plot, and you can see we have two classes. One is blue, another is yellow. The blue class I have represented as 0 and the yellow class as 1. Okay, so now we are going to define our logistic model. So it is a good practice to write the sigmoid function as a separate function, and that's what I have done here. And what this function returns, well, it returns actually an array containing the sigmoid of the input array. Okay, and this is our actual logistic model, and I have called this function as hx, and this returns an array containing the predictions of our input array. So there are two arguments you can see. W represents our vector of weights and X represents our matrix of features. So it just takes this weight vector and matrix of features and then produce a vector that contains our predictions. Okay. And now comes our cost function. As I have told previously, that in this case we are using a binary cross entropy cost function, and this is the formula that I have written in the previous slide. So what we do here, we are taking three arguments, one for the weights, one for the matrix of features, and other for the ground truth outputs. So this y is the ground truth outputs, and first we just declare a variable in ypred and assign the prediction values, and then we use this ypred variable to calculate the error for each one, and then we sum them as our binary cross entropy function asks us to do, and then we return the value. And now comes the interesting portion, that is gradient descent, where we will be minimizing our binary entropy cost function such that we are going to get the optimal values of the weights. So to implement gradient descent, we are going to do that in two parts. First one is the grad function. Well, grad function takes three arguments: weight, matrix of features, and ground truths. And here I have again for simplicity declared a variable called ypred, which will contain our predictions, and then I have declared an array G that will contain three elements, and in the first element of G I will store the partial derivative of our cost function with respect to W0, and in the second one I will store the partial derivative of J with respect to W1, and in the third one the partial derivative with respect to W2. Okay, and the formulas that we have derived here I am showing you again. So these three formulas, this will go into our first element of G, this will go into the second, and this will go into the third. And finally we are going to return our array containing partial derivatives. So now here we have our descent function where we will be updating our simultaneously updating our weights in each iteration. Okay, so these two lines I have printed here just because to print our first guess. So for, as you know, for gradient descent we need to initialize our w to a random variable, to a random point, and that I'm going to print here, and in this line I'm going to print the cost associated for that initialized w, and then I have declared a variable j and initialize it to 0. Well, j will keep track the number of iterations we are doing, and then we are going to run our while loop, and here wpriv will be updated to wnew. And what is wpriv? Well, actually these two variables wpriv and wnew we are taking as argument just to implement the simultaneous update, and this lr actually is the learning rate, which is a hyperparameter for our gradient descent. And in this line we are updating our wpriv with the wnew, and wnew is actually the value of the updated w from the last step. Okay, and then to implement the simultaneous update, as I have told in my previous videos, we do it by temporary variables, and this w0, w1 and w2 are temporary variables, and in this w0 we are going to temporarily store the updated value of w0, and w1 we are going to store the updated value of w1 temporarily, and w2 will do the same for w2. And the formula is pretty straightforward for any gradient descent algorithm, that is the wpriv 0 minus learning rate times gradient, that is the partial derivative of j with respect to w0. And in these two cases, w1 and w2, we are just going to replace the the 0 by 1 and 2, and here we are going to update the wnew, that is we are going to update our weights at one go, at simultaneously, and after that we are going to print our updated value of w and the cost corresponding to that weight. Now we need to have some stopping criteria, okay, because you know that gradient descent, if we don't use the stopping criteria, then gradient descent will run infinitely unless the memory is full. So we really don't want to get into that infinite loop, so that's why we need to stop it somewhere. So what stopping criteria I'm using? Well, I'm using the one stopping criteria is if the distance between two w's, and remember the w is a vector which contain three elements, so we are going to find the distance between two w, that is wnew and wpriv, and if it is less than 10 to the power minus 6, then it will return the current value of w. And other criteria I am having here is that if the number of iterations crosses 100, then we are going to return the w. This line is just counting the iterations. And one thing I really should mention here, that binary cross entropy function is not a convex function as it was in case of squared error. So in that case of squared error, we will be converging to a minimum, and that is the global minimum, because all convex functions have only one global minimum or maximum. But as it is not a convex function, the binary cross entropy function may have multiple minima or maxima. So our gradient descent may stuck into a local minima that is not the optimal minima. So that is a problem with binary entropy cross function. Our gradient descent algorithm may converge to different values if we use different initial values. Okay, so now I'm just going to initialize the parameters, and here I'm just going to initialize everything to 1, and then we are going to train our model. Well, before just running this code, I'm going to run all this code section here. Okay, and now the moment of truth, we are going to run our gradient descent. Okay, you can see that our gradient descent actually worked, because You can see that every step we are decreasing our cost. And let me just scroll down and what we get our at last. So this is the cost, and see one interesting thing here, that the cost is actually oscillating at last few iterations. So why it is happening? Well, this is happening because because of our learning rate, and because the cost function we are using here is not actually a convex function, and we had to stop at some point. So at the stopping point, our cost is that and our weight is that. So let us visualize the result, and let's see if this actually worked. Okay, so this is the visualizing the result portion. So the first thing here is the graph. So you can see that here is a line, y is equal to formula x. So what is that? Well, actually this formula function is what is doing is actually used to plot a line according to our weights. That is, the equation of the line we are plotting here is w0 plus w1 x1 plus w2 x2 is equal to y. So this is just we have plotted here, and again to visualize the result we need to again plot the scattered plot that we have plotted earlier, that is this one. So what we are going to do, we are going to first plot this one, and on top of that, by using the weights, we are going to draw a line. So again, this code is not really that much necessary. You can find it on my GitHub repository. Okay, so let me just run this code, and voila. So you can see that we have got this line, and by just eye estimation we can easily say that this is actually the line we wanted, because anything and everything this side of this line is categorized as 0 class, and anything and everything this side of this line categorized as 1 class. And so that is how you can implement the logistic regression in Python without using any libraries, just from the basic gradient descent. And that was all for this video. If you like this video, then please like and share this video, and please subscribe to Normalized Nerd, and thanks for watching.